Hello friends, welcome to this session. Today we are discussing behavior of gases at high pressure and Boyle temperature. The scientist K. studied the behavior of real gases at a very low temperature in detail and found that at the given temperature their state can be represented by very well by giving the relation between pressure and volume, and that is the empirical relation. So here's the nature of isothermals between PV and P. On the x-axis we are taking the pressure, and on the y-axis we are taking the pressure volume. And this isothermals for various gases have been drawn, and the general nature of the curves as shown in this figure. So above this red dashed line there is the Boyle temperature, and below there this line some changes of the gases. So here we studied the behavior of a gas. The general nature of the curve is same for all gases. At a high temperature, the value of PV decreases initially with increase in pressure. Means यहाँ पे हम क्या कर रहे हैं कि as we are increasing the pressure, what happens? The behavior of gas is initially the value of PV is going to decrease for a particular point as we are increasing the pressure, and it reaches to minimum. वो उसके minimum point तक वो decrease होता है at a particular pressure like this यहाँ पे and then increase with increase in pressure. As we are increasing the pressure, the PV also increases. At lower temperature ये पूरा होता है, but at the temperature below the critical temperature there is sudden decrease in the value of PV. यहाँ पे sudden decrease हो रहा है, इस value पे sudden decrease हो रहा है with is increase in pressure. This corresponds to change the state from gas to liquid. When the liquefaction is complete, यहाँ से यहाँ तक वो प्रोसेस होता है liquefaction का. PV gradually increases with increase in P. This shaded area represents the region of liquefaction. So at a high temperature, here PV, this side, increases with increase in P, but this side means at lower temperature the PV decrease initially with increase in P, but this increase, nature of increase is different for different temperature. So at a lower temperature the changes is maximum changes occur, and as we are increasing the temperature the changes are minimum there. So this line or this decrease, initial decrease, representing the change of state of gas to liquid. So this region is nothing but the liquefaction region. Yeah. So the Boyle law, PV is equal to RT. This is the Boyle's law. Is obeyed only under ideal conditions. That is high temperature and low pressure. That attempts These attempts were made to modify Boyle's law based on the experimental results of Andrews, Amagat, and Holborn and K. Owens. So K. Owens suggested for all real gases at a high pressure and at a constant temperature, an empirical relation is set up. That empirical relation is PV is equal to A plus BP plus Cp square plus dP square plus so on, where A, B, C, D are constants for a given temperature depending on the nature of the gas and are called as viral coefficient. Here A is the first viral coefficient, B is the second viral coefficient, C is the third viral coefficient, and so on. These coefficients are in decreasing order of magnitude. That is, A is less than B, B is less than C, C is less than D, and so on. The ratio of B by A is the order of 10 to the power minus 3, while C by A is of the order of 10 to the power minus 5. So here A is simply equal to RT, because as P tends to 0, this empirical equation becomes negligible in comparison to first at very low pressure and then gases obeys Boyle's law accurately. It means lower the pressure, higher is the degree of accuracy. Holborn and Otto found that up to 100 atmospheric pressure in the temperature range of minus 180 degrees centigrade to 400 degrees centigrade only, for viral coefficients are sufficient to represent the correct behavior of the gas. At ordinary temperature, B is negative for oxygen and nitrogen, air, etc., while it is positive for hydrogen and helium. As the values of A is taken as RT, all other coefficients are smaller than this and decreases very fast with its increasing order. Here the second viral coefficient B is most important. It varies monoatomically for all gases. At the second viral coefficient, or we can say by the second coefficient, at low temperature it is negative. On increasing the temperature, it slowly increases, becomes 0, and then turns positive. The temperature at which the viral coefficient B is equal to 0, here it happens here. So B is equal to 0 is called the Boyle temperature for the given gas. Because at this temperature, the gas follows the Boyle's law up to very high pressure, provided the coefficients C and D are negligible. So PV is equal to constant. Suppose we are taking dou by dou P into PV is equal to B plus 2Cp plus 3dP square plus so on. Such type of equation is used to explain the behavior of real gases. At a low temperature, B is negative because of this one. If the term Cp square dP cube are treated negligibly on increasing P pressure, the product of pressure PV will decrease at low temperature. But at high pressure, the term Cp square and dP cube also becomes finite, and finally the value of the product PV starts increasing with increase in P. At the boil temperature, B is equal to 0 and the other terms are negligible. Therefore, PV is equal to A, that is the constant, and that equals to RT. Therefore, at ordinary pressure, the gas obeys Boyle's law and the PV versus P curve is parallel to the pressure axis here. Is closely parallel to the pressure axis. As we are increasing the P, PV also increases. But for the larger pressure, the second term Cp square becomes appreciable and the product PV starts increasing. Above the Boyle's temperature, above this dotted line, B is positive. Therefore, the product PV starts increase with increase in pressure right from beginning. यहाँ से शुरुआत होता है उसका above the Boyle's temperature. Below the Boyle's temperature or the lower pressure, what happens? The liquefaction starts, and after that liquefaction completed, again the P is increases, PV also increases. But as we are increasing the pressure, this is going to parallel to the pressure. But above the boil temperature, from beginning it going to increases. As we are increasing the P, PV also increases. So this is the behavior of gases at high pressure. Here we are considering the B is important. So this B is nothing but Boyle's temperature. How we can calculate the Boyle temperature at B? The coefficient of B has a special importance for all gases. It varies in similar manner for all gases. It varies similar manner. Its value is negative at a low temperature, but gradually increases to 0 and becomes positive as the temperature is increased. The temperature at which coefficient of B is 0 is called Boyle's temperature and is represented by TB, T suffix B. At this temperature, Boyle's law holds good for, or Boyle's law holds good over a wide range of pressure provided the constants C, B and so on and are all negligible. Thus at Boyle's temperature, B is equal to d by dP in bracket PV is equal to 0. From van der Waals equation of state for a real gas, and that is the corrected, later on we discuss on this van der Waals equation. Before this starts, so consider PV is equal to A, that is the constant. That is nothing but the Boyle's law. It obeys the Boyle's law. So according to van der Waals equation of state for real gas, P plus A by V square in bracket V minus B is equal to RT. So this is the corrected formula. Later we discuss in particular in a special session, that is the van der Waals corrected equations. Here the term A and B are the van der Waals constants. Solving equation 3, we get PV minus PB plus A by V minus AB by V square is equal to RT. PV is equal to RT plus PB minus A by V plus AB by V square. Just we rearrange this equation. So PV is equal to RT by we are taking the we can approximately write this equation, that is V is equal to RT by P. Putting this value of V in equation 4, so we get PV is equal to RT plus PB minus A by RT into P plus AB by R square T square P square. Just rearrange it and simplify it. We get RT plus B minus A by RT into P plus AB by R square T square into P square. Comparing this with viral equation of state. Viral equation is nothing but PV is equal to A plus BP plus CP square plus DP square and so on. Just compare it. We get the value of A, value of C, value of B. So here A is equal to RT, B is equal to B minus A by RT and C. So here this value is A here, this value is B here, and C value AB by R square T. Just we are putting the value by comparing this equation. P is equal to RT is nothing but A, B minus A by RT is equal to B, AB by R square T square is C. At Boyle temperature, what happens? T is equal to TB. So all these T's are the Boyle's temperature. So and B is equal to 0 we are taking. Then equation is what? 0. किस ये वैल्यू क्या होती है? इस वैल्यू की वैल्यू हो गई 0 because B is equal to 0. Substitute किया मैंने. Then we get TB is equal to R goes to this side. So we get A by RB, and this is the Boyle temperature. So this is the equation gives the value of Boyle's temperature for all gases obeying van der Waals equation of state. Here the Boyle's temperature depends upon the value of A and B, which are the different for different gases. Suppose we are taking the nitrogen gas. The Boyle temperature of the nitrogen gas is 50 degrees centigrade, and for hydrogen it is minus 169 degrees centigrade, while at the helium it is minus 2.4 degrees centigrade. Then what is the behavior of gas above, below and at Boyle temperature? For this, just plot this graph against the product PV against the P. Here the three lines are there. First, pink color is represented as the Boyle temperature, then orange color is represented as the below Boyle temperature, and this line curve is representing the above the temperature. The general nature of curve is same for all gases. So first what happens? इस लाइन के नीचे क्या होता है इनिशियल स्टेट में? द वैल्यू ऑफ पीवी ये क्या हो रहा है? डिक्रीज हो रहा है एज वी आर इंक्रीजिंग द प्रेशर. सो इट बिगिंस टू इंक्रीजेस. ये क्यों हो रहा है? बिकॉज ऑफ हाई प्रेशर. हाई प्रेशर की वैल्यू क्या होती है? द टर्म्स लाइक Cp square dp cube etc. सो अब जो आपका इक्वेशन है कौन सा एम्पेरिकल इक्वेशन, दैट इज द पीवी इज इक्वल टू ए प्लस बी पी प्लस सी पी स्क्वायर प्लस डी पी स्क्वायर प्लस सो ऑन, बिकम्स मोर इफेक्टिव एंड आर पॉजिटिव, एंड दस यहाँ आने के बाद पॉजिटिव बनता है और वो इंक्रीज होता है, दस इंक्रीजेस पी वी विथ इंक्रीज इन पी आफ्टर रीचिंग अ मिनिमम, ये आपकी उसकी मिनिमम वैल्यू है। इसी वैल्यू को हम उसकी क्रिटिकल प्रेशर बोलते हैं। अगर इसी को हम इसके यहाँ पे लेंगे, सपोज दिस वैल्यू इज द critical pressure of this one. So what happens? What happens actually at below the temperature, Boyle temperature, this term, the temperature is less than Boyle temperature. This suggests that the existence of intermolecular attraction because below TB the gases are highly compressible. Now we are considering this above Boyle's temperature. T is greater than Boyle's temperature. PV continuously increases with increase in P because the coefficient of B is positive above Boyle's temperature, and thus the terms on right hand side of the empirical equation are positive. It indicates that intermolecular attraction is now less significant. Then third, that the Boyle temperature, T is equal to TB. The product PV is almost constant for a long range of pressure. Thus Boyle's law is obeyed over a wide range of pressures. Thus below the Boyle's temperature, the gases are highly compressible, and this suggests the existence of intermolecular attraction. Beyond the Boyle temperature, Boyle law is obeyed and intermolecular attractions are less significant. From this concept, we can define the Boyle temperature. Boyle temperature is that temperature above which a real gas behaves like an ideal gas and obeys the Boyle's law. So this is the behavior of gases at high pressure and Boyle's law, Boyle's temperature. So thank you very much for watching this video.